Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today I want to discuss about definitions and terminology of torsional loads. So what are the important definitions and what are the terminology required for torsional loads while solving problems and while deriving equations? You should know some important definitions and terminology. So today we will see this topic related to this definition and terminology related to torsional loads. First of all, you should know about the course outcome. So that is the topic outcome of this module. The students, after completion of this course or module, the student should be able to analyze the theory of fluid torsion and bending to draw, shear stress distribution diagrams in circular shafts and bending moment distribution diagrams in various cross sections of beams for different loading conditions. So after completion of this module, the student can able to analyze. So already they have learned the fluid torsion equation derivation and how to draw the shear stress distribution also completed. And the problem solving also over. Now the finally, so the definitions and terminology, important terminology and definitions. After completion of this topic, the student should be able to answer all things related to this fluid torsion. So first of all, the definition of torsion. So how do you define the torsion? So consider a shaft rigidly clamped at one end and twisted at the other end by torque, that is force multiplied with the distance, applied in a plane perpendicular to the axis of the bar. Such a shaft is said to be in torsion. So torque is equal to force multiplied with the distance. See here, a shaft rigidly clamped at one end and twisted at other end. Clear? So here the force applied and how much distance? That is the diameter of the shaft. The plane perpendicular to the axis of the bar. So axis of the bar is, and the plane is, the force applied plane is perpendicular. So this type of phenomena is known as torsion. So here example given for circular shaft. So next, what are the effects of torsion? The effects of a torsion load applied to a bar are to impart an angular displacement of one end, a cross section with respect to the other end, to set up shear stresses on any cross section of the bar perpendicular to its axis, to impart an angular displacement with respect to the one end to the other end. So next one, the important definition is shaft. What do you mean by shaft? And a twisting moment. The shafts are the machine elements which are used to transmit power in machines. So these are the generally circular and cross section used to transmit power in machines, one shaft to another shaft, one place to another place with the help of this shaft. So transmission shafts and then machine shafts also classified into two types. The twisting moment. The twisting moment for any section along the bar, the shaft is defined to be the algebraic sum of the moments of the applied couples that lie to one side of the section under consideration. So the choice of the side in any case is of course arbitrary. The twisting moment for any section along the bar, the shaft is dependent on the algebraic sum of the moments, either one side or one side of the section under consideration. So what do you mean by shearing strain? Next definition. If a generator A to B is marked on the surface of the unloaded bar, then after the twisting moment T has been applied, this line moves to AB. See here shown the diagram. A and B, they marked on this marked on the surface of the unloaded bar. Then after the twisting moment T has been applied, this line moves to A B dash. Move to A B dash. So that is twisting moment. The angle G measured in radians, here the angle gamma measured in radians between the final and original positions of the generators is defined as the shearing strain at the surface of the bar or shaft. So the same definition will hold at any interior point of the bar. See, here generators are A point and B. AB is one line and A and B dash is the twisting moment. Angle. So how much twisted with the angle gamma. Next one is modulus of elasticity in shear. So already we have seen in simple stresses and strains E, Young's modulus. Here also the modulus of elasticity in shear, the ratio of the shear stress to the shear strain is called the modulus of elasticity in shear or modulus of rigidity and is represented by the symbol G. So according to Hooke's law, stress directly proportional to strain, stress is equal to E multiplied with strain in the case of tensile. Here in shear, the stress is shear stress and the modulus is shear modulus and the strain is shear strain. So that you can write G is equal to tau by R. So the angle of twist. If a shaft of length L is subjected to a constant twisting moment T along its length, then the angle theta, not Q, theta, through which one end of the bar will twist relative to the other. This is known as angular twist. So already we have seen in a previous case. Next one is relationship. What is the relationship in the torsion theory? In simple torsion theory or development of torsion formula. So very important this torsion equation. So what is torsion equation? Write down the torsion equation. So like that they will ask in examination. So that you have to write T by J is equal to tau by R is equal to G theta by L. So one by one we will see what is this first term, what is this second, what is this third term. So this is very important, the terminology related to this simple torsion theory. The first term, it refers to applied loading and a property of section. So here, which in the instant is the polar second moment of inertia. In the T by J in a derivation already we have seen the torque and then polar moment of inertia. The second term is, this refers to the stress, and the stress increases as the distance from the axis increases. G is equal to, already we have seen in the first case, G is equal to tau by shear strain. So this refers to stress, and the stress increases as the distance from the axis increases. So third term is G theta by L. It is a deformation related to the deformation and contains the terms modulus of rigidity and a combined term, the theta by L. In G theta by L, take this term, which is equivalent to strain for the purpose of designing a circular shaft to W withstand a given torque. We must develop an equation giving the relationship between twisting moment, the maximum shear strain produced in a quantity representing the size and shape of the cross-sectional area of the shaft. So already we have derived that the equation. So that T by J is equal to tau by shear strain is equal to G theta by L. So this is the torsion equation. Next definition is torsional stiffness or tensional stiffness. So tensional stiffness or torsional stiffness. The actual word is torsional stiffness. Torque per radius twist. So that is K is equal to T by J is equal to G theta by L is equal to tau by gamma. The torsional stiffness K is equal to load for deflection. So to load, torsional load, and deflection is theta. So you can write T by theta is equal to Gj by L. Next, power transmitted by a shaft. If torque is the applied torque T and W is the angular velocity, omega is the angular velocity of the shaft, then the power transmitted by the shaft is P is equal to torque multiplied with omega, angular velocity. That is 2 pi nt by 60. So in this, n already you know, that is speed of the shaft, and T is the torque applied, divided by 60 into 10 cube, convert into kilowatt. So n is here RPM. So that the torque P is equal to 2 pi nt by 60. 2 pi nt by 60 in kilowatts. Kilowatts, 10 cube into kilowatts. Next, torsion of hollow shafts. How do you calculate the torsion of a hollow shaft? You know the hollow shaft having two diameters, sectional and internal diameters, whereas in solid shaft only having single diameter. So from the torsion of solid shafts of circular section, it is seen that only the material at the outer surface of the shaft, already I told you, can be stressed to the limit assigned as an allowable working stresses. But in this case, in the hollow shaft, all of the material within the shaft will work at lower stress and is not being used to full capacity. So in these cases where the weight reduction is important, so advantages to use a hollow shaft. So here, whatever taken assumptions, Same assumptions will be made as in the case of solid shaft. Whatever you take an assumptions, here also apply for hollow shaft. So general torsion equation applied. Here general torsion equation T by J is equal to tau by R is equal to G theta by L. So this is general torsion equation. So for the hollow shaft, the J. So for the solid shaft, J is equal to pi d to the power of 4 by 32. For solid shaft. For in the case of hollow shaft, d naught is outside diameter and di is inside diameter. So you can write the letter di is equal to d naught by 2 half of the outside diameter. So j is equal to pi d naught to the power of 4 minus di to the power of 4 by 32. The tau maximum or solid is equal to 16T by pi d naught cube for solid shaft. Why? Because it is having only one outside diameter. So actually the T is equal to pi by 16 into d cube into tau. So from this equation you can write the shear stress is equal to 16T by pi d cube. Clear? D is the outside diameter. But in the case of hollow shaft, T into d naught by 2 by pi by 32 into d naught to the power of 4 minus di to the power of j. J is polar modulus, section modulus, polar modulus. Now simplify this equation. 16T into d naught by pi d naught to the power of 4 multiply with 1 minus di by d naught to the power of 4. Now finally we will get 1.066 into 16T by pi d naught cube. So the weight of the hollow shaft. So the weight of the solid shaft and the reduction weight you have to calculate. The weight of the hollow shaft, area multiply with length and density. So pi d naught square by 4 minus pi d naught by 2 by 4. So why? Because this is di. Di is equal to d naught by 2. So pi d naught square by 4 minus pi d naught whole square by 16 n into rho. So now finally you will get 0.75 p d naught square by 4 into L into rho. So weight of the solid shaft is pi d naught square by 4 multiply with L into density. The reduction in weight 1 minus 0.75 into pi d naught square by 4 into L into rho. So now finally we will get 0.25 pi d naught square by 4 multiply with L into rho, the density. The torsion of hollow shafts, hence the reduction in weight would be just 25%. See here, So general torsion equation applied for this case, and here the weight reduction is important. So all of the material within the shaft will work at a low stress and not being used to full capacity. So that where the weight reduction is important, it is advantage to use hollow shaft. So the hollow shaft, so having a hollow inner diameter and external. In the case of solid shaft only having outer. So here di and the outer diameter d naught. So in this case, we are considering the weight is advantage use of the hollow shaft instead of using the solid shaft. The weight is higher. So that's why you have calculated here weight reduction through the torsion equation. So the weight of the solid shaft is pi d naught to the power of 4 by so square by. So it means pi by 4 d square area multiplied with L into rho. Clear? So reduction in weight in the case of hollow shaft, this is solid shaft, and hollow shaft is we got 0.25 pi d square by 4 into L into rho. So it means in solid we got pi by 4 into d square into L into rho. So that is weight of the solid shaft. So the weight of the hollow shaft is 0.75 times of the solid shaft. So here what will happen here? Reduction. How much reduction in weight? So that 1 minus 0.75 into pi d naught square by 4 into L into, so finally you will get 0.25 pi d square by 4 multiplied with L into rho. So this is the reduction in weight when compared to hence the reduction in weight would be just 25%. Clear? Next, definition and terminology of springs. So in this, in springs, whenever subjected to some force, so inside the springs also some shear stresses will be induced due to the torsion. So some important definition and terminology you should know about these springs. Springs are the elastic bodies which absorb energy due to resilience. The absorbed energy may be released as and when required. Whenever you want that energy you can release. So it means some amount of energy stored inside the spring due to the elasticity property. A spring is which is capable of absorbing the greatest amount of energy for the given stress without getting permanently distorted is known as the best spring. So there are two important types of springs. How many types of springs are there? One is laminated leaf spring and helical spring. So define laminated spring or leaf spring. So what is this laminated spring or what is leaf spring? Both are same. So near laminated spring for your understanding. So the laminated springs are used to absorb shocks in railway wagons, coaches and road vehicles. shows a laminated spring which consists of a number of parallel strips over a metal having different lengths and same width placed one over the other. So length is shown here between one end to another end, the main strip, and some more springs and laminated plates are attached to this main one. So whenever the shock loads observed, then it will deflect delta. So next, closed coil helical springs. So definition: a spring may be defined as an elastic member whose primary function is to deflect or distort under the action of applied load. It recovers its original shape when load is released. So whenever the load is removed, it regains its original shape. The springs are energy absorbing units whose function is to store energy and to restore it slowly or rapidly depending on the particular application. So this is the actual definition of closed coil helical springs. Next, important types of springs are, there are various types of springs. One is helical spring. They are made of wire coiled into a helical form. The load being applied along the axis of the helix. In this type of springs, the major stresses is torsional shear stress due to twisting. So the major stresses are torsional shear stress. So they are made of wire coil like this. They are both used in tension and compression. Next, spiral springs. How do you define the spiral springs? They are made of flat strip of metal wound in the form of a spiral and loaded in torsion. So in this, the major stresses are tensile and compression due to bending. So the spiral spring shown in figure. Next, uses of springs. What are the uses of springs? To apply forces and to control motion as in brakes and clutches, and to measure forces as in spring balance, to store energy as in clock springs, to reduce the effect of shock or impact loading as in carriage springs, to change the vibrating characteristics of a member as in flexible mounting of motors. These are the uses of springs. Next, spring deflection. So what is the formula? So you can write the spring deflection, X are delta AW d cube into N by G d to the power of 4. The D is coil diameter and small d is the wire diameter. N is the number of coils, W is the load applied, and G is the modulus of rigidity. Spring stiffness. The stiffness is defined as the load per unit deflection. The stiffness is defined as the load per unit deflection. K is equal to W for W upon delta or X So already we have calculated delta is equal to 8W d cube into n by g d to the power of 4. Here W is load, capital D, coil dia, and N, number of coils, and G, modulus of rigidity, and small d, wire dia. So these are the abbreviations in this deflection formula. So therefore, you can calculate the stiffness, that is K, G d to the power of 4 by 8 d cube into N. Next, shear stress. So how do we calculate the shear stress? So you can write this formula by using torsion formula. Torsion formula already have learned. T by J is equal to tau by R. So here torque is W multiplied with D by 2, that's radius, and J is polar moment of inertia, that is pi d to the power of 4 by 32 into tau by R is D by 2. So this is equation written by using torsion formula. Now the shear maximum, find out. The shear stress is equal to AWD by pi d cube. So next, Walls factor. What is this Walls factor? In order to take into account the effect of direct shear and a change in coil curvature, a stress factor is defined. That is known as the Walls factor. So the Walls factor is 4C minus 1 by 4C minus 4 plus 0.615 by C. What is C here? C is the spring index, that is the ratio of coil diameter to wire dia, D by D. So we will use Walls factor. So why should you use this one? The effect of in order to account the effect of direct shear and change in coil curvature. Whenever you are considering curvature effect, then the Walls factor you must use while solving problems. So that is denoted by capital K. Next, if you take into account the Walls factor, then the formula for the shear stress, normally shear stress written from this 5 by 16 into tau into d cube. You are considering 16T multiply with Walls factor, 16Tk by pi d cube. Tau v is equal to 16T into K by pi d cube. So next, strain energy. Strain energy is defined as energy which is stored within a material when the work has been done on the material. So in this case of spring, the strain energy would be due to bending, and the strain energy due to bending is given by the expansion, that is U is equal to T square L by 2EI. L is pi dm and pi d to the power of 64. After substitution, we get 32 T square dn by E d to the power of 4. That is the strain energy. Next, in this case, the bending moment is constant throughout the spring and is equal to the applied axial torque T. The stresses, that is the maximum bending stress, may thus be determined from the bending theory. So that is sigma max is equal to my by I. So m by I into sigma by y is equal to E by R. This is the bending equation. So already we have derived. So now write down this equation. Take these two terms written in this form, sigma max is equal to my by I. So m is the t into d by 2 by pi d to the power of 4 by 64. The sigma max is equal to 32 t by pi d cube. Next, deflection or wind up angle. What is this wind up angle? Under the action of an axial torque, the deflection of the spring becomes the wind up angle of the spring, which is the angle through which one end turns relative to the other. So this will be equal to the total change of the slope along the wire. So according to area movement theorem, this is called as a wind up angle. Whenever the torque is applied, how much the twisted, how much turned that coil. So that angle is wind up angle. So you can measure by using this formula. Theta is equal to 64t into d into n by e d to the power of 4. So the derivation part. So final equation you can write theta is equal to 64t into d into n by e d to the power of 4. T you know torque and d is the wire coil diameter, mean coil diameter, and n is number of coils, number of active coils, and e is the Young's modulus, and d is the wire diameter. Next, springs in series. When the springs are connected in series, so how do you calculate the stiffness? If two springs of different stiffness are joined end on and they carry a common load W, they are said to be connected in series, and the combined stiffness or deflection given by equation 1 by k is equal to 1 by k1 plus 1 by k2. You can write k is equal to k1 k2 by k1 plus k2. The stiffness of one spring and another spring stiffness k2. Similarly in parallel, so if the two springs are joined in such a way that they have a common deflection x or delta, they are said to be connected in parallel. So as shown in figure. So in this case, the load carried in shared between the two springs and the total load W is equal to W1 plus W2. So now we can write the deflection is, stiffness is the load for deflection and deflection is load for stiffness. So W1 by K1 is equal to W2 by K2. So further the W is W1 plus W2. So thus K, the total stiffness is K1 plus K2. So the stiffness in the case of parallel is K1 plus K2. In the series, K is equal to K1 K2 by K1 plus K2. So like this, how to write. So these are the definitions and terminology important related to the torsional loads. So these are the references I have taken. Yes, Ramamritam, the other name, and then strength of material title of the book, Dhanapati Rai Publishing Company, and R.K. Rajput. Title of the book is Strength of Material, S.N. and Co. And R.K. Bansal, a textbook of Strength of Material, Lakshmi Publications. And R.S. Kurmi and Gupta. These are Strength of Material title, and publishers are H.N. and Code, S.N. and Co. And these are the references I have taken for this PPT. Take any one reference and further more clarification. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.